Our next topic is the P chart. We use the P chart to monitor the proportion of defects. We have two key questions in mind. How can we construct the chart, and how can we use the chart to decide whether the process is in control or not? I want to take an example and show you how to construct a P chart. Hometown Bank is concerned about the proportion of customer accounts recorded wrong. Each week, a random sample of 2,500 accounts is taken, and the number of accounts with incorrect deposits is recorded. The following data are collected when the process is believed to be in control. So in the first week, we took a sample of 2,500 accounts, and of these 2,500 accounts, we counted how many of them are recorded wrong, and we found out 10 of them are recorded wrong. So does this mean we only have 25 accounts in this bank? No, we just sampled some of them. We sampled 2,500 accounts. So that's the sample size, n equals 2,500. And we repeat this every week. In the second week, we collected another 2,500 accounts. Of these 2,500 accounts, we found 17 accounts that are recorded wrong. So part A, compute the control limit, upper control limit and the lower control limit of the P chart. In the P chart, in the x-axis, we're going to put every week. And on the y-axis, we're going to put the sample proportion. So, and we also have the upper control limit and the lower control limit. And part A is concerned with computing these limits. To compute these limits, we're going to use the following formulas. P bar plus 3 times the square root of P bar 1 minus P bar over N. Now, how can we compute P bar? We know what N is. N is the sample size, which is 2,500. And how can you compute P bar? To compute P bar, we need to compute the sample proportion of each sample. The sample proportion is the proportion of defective accounts in a sample. So for sample number 1, of 2,500 accounts, we found 10 defective accounts. What's the proportion of defective accounts? 10 over 2,500, which is 0.004. And we repeat this for each sample. For sample number 2, we had 2,500 accounts. Of these, 17 were defective, 0.0068. Next, 15 over 2,500, 0.0060. Next, 3 over 2,500, 0.0012. This P-bar is the average of all the sample proportions. It's the average of all these numbers, so add them up, divided by 4, we get 0.0045. Okay, so that's P-bar, and we can plug this into the formulas. P-bar is 0.0045, and N is 2,500. So if you plug them in, you get 0.0085, which is the upper control limit, and 0.0005, which is the lower control limit. So in the P chart, the x-axis is the sample number, the y-axis is a sample proportion, and the upper control limit is 0.0085, and the lower control limit is 0.0005. B, the bank kept collecting samples as follows. Is the process in control according to the P chart? We already have the P chart. We calculated in the previous part. So you want to use this chart to make a decision. So we kept collecting samples in the following weeks. right? In the following week, we collected 2,500 accounts. Of these accounts, 24 of them were defective. So what should we plot on the P chart? So in the P chart, we need the y-axis is the sample proportion. So we have to compute the proportion of defective accounts in each sample and plot that. So proportion of wrong accounts is 25 over 2,500, which is 0.0096. And again, 15 over 2,500, 0.0060. And again, 26 over 2,500, 0.0104. And we can plot these sample proportions on the P chart. So the first one, 0.0096, is below, actually compared to the upper control limit, 0.0096 is above the limit. And the next one is 0.0060, that's below the upper control limit. And the next one is 0.0104, so that's above the upper control limit. Now we can make a conclusion. Is this process in control or not? Since we have two sample proportions that are outside the limits, the process is out of control. That's our conclusion.